Okay, so we're going to be looking at the section about exploring accumulation of change and Riemann and trapezoidal sums. And so let's take a look at this. What do we mean by accumulation of rate of change? Well, up until now, we've been given functions and asked to talk about the rate of change, which is the derivative. And so what we're going to be looking at now is we're looking at, if I give you the rate of change, okay, can I ask questions about the original function from that? Okay, besides what we've already done, increasing or decreasing, can I find information about it that can be useful in other aspects of things? So here's a velocity connection. As we know, velocity is the rate of change of the position with respect to time. If we know the velocity, can I recover information about the position? Can I figure out where I'm at? So let's look at a problem with a constant velocity. Find the distance traveled. So a truck has a constant velocity of 60 miles per hour, and you're going to travel that for 1.75 hours. How far did it go? See, that's what we're talking about. So how far did I travel? Well, take a look at it. If I look at this thing as an area, I can graph the velocity function, which is a constant 60 miles per hour. I'm going to travel that for 1.75 hours. And we know that the distance is equal to the rate times the time. So if you look at this closely, the distance I traveled in is the rate, which is 60 miles per hour, for 1.75 hours, and that becomes the area under the velocity curve in that region. And so we're going to look at that concept of how the area under the curve helps me determine how far I have traveled. That's pretty easy if it's a constant. But what if it's not constant? So what if I have a variable velocity? So here's the story now. So now I have a truck, and it's going to slow down for an exit ramp. Here's the velocity. So I went from 60 miles per hour, and I slowed down to 30 miles per hour, and I did that in 10 seconds. How far did the truck travel over those 10 seconds? Okay, so how can I figure that out? Well, let's take a look at it. If the velocity is the area under the curve, that would be this thing right here, this area all the way down. Okay, and so how do I find that area? Well, that area is a trapezoid. So it's the shape of a trapezoid. So the formula for the trapezoid is 1/2 the base 1 plus base 2 times the height. Okay, but we have to make sure we have proper units. This is the unit in miles per hour, and this is a unit in seconds. They have to agree. Your time units have to agree, which means I'm going to take the 10 seconds and change it to an hour format. And that's this part right here. So there's 3,600 seconds in an hour. So 10 seconds is 10 out of 3,600. This base right here is 60. This base over here is 30. And so that's, you add those together, cut it in half, and then times it by this height. And I get 1/8 of a mile. That's how far it traveled. Okay, so be careful of your units, and that is 10 seconds as an hour, so you know. So that's what we're talking about. So here's this one. Well, what if the velocity is variable and it's not linear? So this was a linear velocity. This was a linear velocity. What if it's not linear? Okay, what's going on there? Well, let's take a look. So what if I have something like this? Here's my velocity curve. Some above, some below, and all that kind of stuff. We still need to find the area, which tells us the change in position. We'll do ones like this pretty soon. But we can talk about it already. So the area of a region between a velocity graph and the t-axis can be interpreted as the change in position. When the region is bounded by the velocity graph and the t-axis is below the t-axis, we have a negative velocity. Okay, the motion is in a negative direction. Okay, so let's look at some examples of some things. I got it. So here is an example that we're going to be looking at. All right, the function r of t models the rate of change of the altitude of a helicopter in feet per second, where t is measured in seconds. How much altitude did the helicopter gain from 0 to 8 seconds? And the other question is, what is the net change in the helicopter's altitude over these 16 seconds? So the area between, between 0 and 8, so between here and here is this area right here. And that shape is a triangle. So you can use the formula for the area of a triangle to help us answer this question. So for part A, the answer is going to be the area is 1/2 the base times the height. The base is from 0 to 8, so that is 8. The height is from 0 to 40, so that is 40. And so we multiply this out, and we get 160 feet. So that is how much altitude the helicopter gained. It went from 0, in this case, went from 0 to 160 feet. Part B. What was the net change in the helicopter's altitude over the 16 seconds? So if this is a rate, think about the stuff we learned. This is where it changes, because it changes direction, right? It was increasing here and then decreasing here. And this is where it reaches maximum altitude. So the helicopter, this is the rate, this is the speed of the helicopter, the velocity. So it was going up and then it was coming down, kind of a thing. So what's going on here? Well, it's this area, and this is below the t-axis. So this down here is going to be subtracted from the other one as a net change. So the area now is the 160 feet from the first half minus the area of this triangle. So this is 1/2 base times the height. The base is another 8, and the height is 20. That's 20. Not negative 20, because we're doing an area as a solid piece. This is how much it went down. That's why it's negative. Negative here would have been down. And so what is the net change overall? 80 feet is your net change. Okay? So let's take a look at another example. This graph right here gives the velocity in feet per second of a car for t between 0 and 8 seconds. T is measured in seconds. What is the estimate? What is an estimate of the distance traveled by the car from 0 t equals 0 until the car comes to a stop? Okay? So what is that? It's an estimate. So we look at this over here and we say, okay, well, what could be an estimate for this? And you can look at it however you want. You can look at it as a geometric shape. You can look at it as this right here. And I can look at it as a rectangle. I can estimate it as a triangle. Okay, so it just depends on what kind of estimation you want to look at. I think the way I drew it, it looks more like a rectangle than it would be a triangle, but it doesn't matter. Either way would have been fine. If I look at it as a rectangle, then I have 50 feet per second. This is 8 seconds. And so that is our simple little, the area could be approximately, so let's do approximately 50 times 8 and get 400 feet. Or I can do it as the triangle, and I can estimate the area as 1/2 the 50 times the 8 and get 200. So either one of those is an estimate. Okay, what is an estimate? Well, there's two different ones. It just depends on how I want to estimate this out. Okay. So now what we want to do is we're going to look at how to make better approximations under this curve. So see, these aren't very good. A lot of big gaps over here. It's not really accurate in either fashion. So how do I make a better one? What can I do? What techniques can I do to make this better? All right, and that's going to be a Riemann sum or a trapezoidal sum. Okay, we're going to start with the Riemann sum. before we do the trapezoidal. So the Riemann sum uses the sum of the areas of rectangles to approximate the area under a curve. The trapezoidal sum is the same thing, you're just going to use trapezoids to do it. So let's look at this Riemann sum, okay? Yeah, there we go, Riemann sums. So I got a continuous function f bounded by a, b, and the x-axis. So we're looking at this region right here. A Riemann sum comes in three types: a left, a right, and a mid. And I'll explain what those mean here in just a moment. Since the Riemann sum adds the areas of rectangles, which is basically the areas of base times the height, the left, right, and mid describe what part of the top of the rectangle touches the curve. So for example, I'm going to draw little rectangles in here, a bunch of them. And I'm going to make, if it's a left Riemann sum, the left side of the rectangle is going to touch the curve. The right will be above or below, depending on the situation. If I have a right, then the right side of the rectangle will touch the curve. And if I have a mid, then the midpoint of the rectangle will touch the curve. You need to be familiar with all three aspects of this. And so we will explore all of those as best we can. So that's that. So let's look at a left Riemann sum of this problem up here. So here's what it basically looks like. I'm doing a left to illustrate my point. Okay? I know it looks kind of complicated, but watch closely what's going on. Here's the function from A to B. Okay? And so this would be, each of these little segments right here represent some x value. So this one we call x sub 0 for the initial amount. This is x sub 4 because there's 4 rectangles. x0, x1, x2, x3, x4. So it just gives you those numbers there, like a sequence. So the area of each of these rectangles, I'm going to add them up. And so you notice I can get a pretty good approximation with this. There's only a little bit of bleed over the top here in this thing. So it's going to be a little bit larger than normal. But I can get a pretty good approximation with these 4 rectangles. So the base, since the area of a rectangle is base times the height, the base of these rectangles is that distance right there. Okay? It's the change in the x. If the base lengths are all equal, which is what they're going to be most of the time. They don't have to, but they can be. You can make them that way if you have the control of the width of these things. It's the total distance, which is b minus a, divided by how many rectangles I have. So I'm going to cut them up into equally spaced amounts. And so that n is the number of rectangles you're going to use, or what's called subdivisions. The height of the rectangle, though, since it's a left, is I have to take the left side, this value of x right here on the left of the rectangle, and plug that into the function, so that's where, because that's where it touches. And so the height is going to be f of x sub I, whichever one of these things that we're going to do. The value of the function at each of these little x's. So then what I have here is my area of a left Riemann sum is the base, the change in the x, is the base length times the height at A, and then plus the base times the height at x1, and the base times the height at x2, and the base times the height at x3. See? So that gives me the base and the height, 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 and I add up all those numbers. And so when I add them all up, I'm going to get an approximation for this area under this curve. Okay? The height is determined by the x of I that is associated with the left side of the rectangle. If it was a right Riemann sum, then I would be doing the right one. Okay? And so forth. So let's look at this problem that I have right here, and I'll show you how we can do this one all the way through. All right. Here we go. Find the area of the region using a left Riemann sum bounded by this function f of h of x equals e to the x. X goes between 1 and 3 and the x-axis with 6 subdivisions of equal length. So how would I do this problem if I was given this function? Well, I'm going to draw a quick sketch of it. Okay? It doesn't have to be perfect, but it's just used to represent what you're going to do. It is an e function. I'm going to go between 1 and 3. I need to cut this into 6 equal pieces. That means each of these has to be cut up into 2 more. So I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 subdivisions. I don't need to plug them all in there. Okay, just basically I'm just going to plug in 1 and 3. So each of the 1 is like 2 point something, and each of the 3 is going to be, upwards in the ballpark of a little bit less than 27. So it's going to be up here somewhere. I don't know exactly where it is. We can figure it out a little bit later. So what I have is I have an E function that looks like that. Okay, so this is the boundaries of those. Okay, and so what I need to do now is I'm going to do a left Riemann sum. So I'm going to build rectangles in here where the left side is going to touch the curve. See? Then go up from this point up, the left side, touch the curve, go straight across, and come down. Go up, touch the curve, come across, and go down. And you just keep doing this until you have the entire thing drawn. And so these are the key points that I need to look for. Since this is equally spaced, this right here is 3 over 3. So this will be 4 over 3. This is 5 over 3, 6 over 3, 7 over 3, and 8 over 3, and 9 over 3. So I need to make these values. I can use my table to help me figure out those heights. So I have x and h of x, and I'm going to plug in all of those numbers. So I need to plug in a 1. I need to plug in 4/3, 5/3, 2, 7/3, 8/3, but not 3, because 3 is not a left point. So when I plug these into my function, e to the x, don't overthink it. This is just e to all these powers. And right now we'll use a calculator later for finding these values if need be. But I'm just showing you those are all the heights. Those are all the f's. Okay. And so we have the base length is from here to here is a distance of 1/3. So my delta x. Okay. So my delta x is 1/3. These are all f of x's. That's what I'm going to be using. So I'm just going to add up the area of all of these rectangles. So this area of my left Riemann sum is going to be approximately, now it's base times the height, and so I can do each one individually. Take a look over here. See how they all had the delta x in it? So I can factor that out and bring it to the front. So then this is going to be 1/3 times, and then all of these heights. So it'll be e to the 1, e to the 4/3, e to the 5/3, e squared, e to the 7/3, e to the 8/3. And so that represents the area of all those rectangles added together. And that is your left Riemann sum. Okay? So let's take a look. A couple of things I have over here. You can see that I have this written down already. The rectangles do not have to be the same width. Sometimes you'll get problems where you are given a table to describe a function. And when that's the case, you'll use whatever width that they gave you. Okay? So this is how I found the delta x. Just, I can also just look at it here and see it. The whole distance is 3 minus 1. I want 6 of them. So that's how I got 1/3. If the function is kind of, got some weird numbers here, it's harder to find. Let's look at another example that I have. So here's this one. Here I'm given a table of values. Okay. G of x is a constant, continuous function from 0 to 25. G is the rate that the Katie travels from home to school in meters per minute, and x is in minutes. Approximate the distance Katie travels using a left Riemann sum. So I have these distances over here. Okay. Here's what I would recommend that you do. Draw a sketch of this table. Okay. It doesn't have to be accurate or pretty or anything like that, but it does help tremendously in your setup. I'm going from 0 to 2, then I'm going from 2 to 6, 6 to 8, 8 to 15, and then 15 to 20, and then 20 to 25. I want a left Riemann sum, so I'm going to start at 0, and I'm going to go up to the height of 10. So this is the left side of this rectangle, and I put the 10 up here so I don't forget that that's the 10. From 2 to 6, this one is the 2, it's the left. I'm going to go up to 14, go all the way across, and write 14 up here so I know that that's what it is. I'm going to go start here at 6. I'm going to go up and go across, and that's to 20. At the 8, I'm going to go up to here and go across because that is 15. Then I'm going to go from here is the left, so I'm going to go up to 30 and go across. And then at 20, I'm going to go up to 20 and go across, and that completes our thing. So this one is not used because it was a left. We want only the height at the left side of my rectangles. And so you can see here that they're not equally spaced at the bottom, but I have drawn the rectangles, and I just got to simply do a base times the height. So this area can be approximated by doing what? Well, this one, which is base times the height, so it's going to be 2 times 10 plus 4 times 14 plus 2 times 20 plus 7 times 15 plus 5 times 30 plus 5 times 20. And then I can add all that up and get an approximation for this, which comes out to be about 471. And then the units here are in meters, so we want meters. And that's an approximation for the distance she travels to school. Okay, let's look at Katie's story and do a right Riemann sum. Okay, so if you're going to do a right Riemann sum, you're going to do basically the exact same thing again. You're just going to go from the right side. So you want to draw, again, a picture. Always draw a picture. There's the 2, there's the 6, there's the 8, 15, the 20. I'm not drawing it to scale. I'm just drawing it for the representation. So at 2, I'm at 2 now. This is the right side of my rectangle. I have to go up to 14. 6 goes up to 20. 8 goes up to 15. 15 goes up to 30. 20 goes up to 20. And 25 goes up to 10. See, so I went up to here at the, and then it went across that way for right. So take these numbers and add those up for a area of right, and you do the same thing. So it's going to be 2 times 14, 4 times 20, 2 times 15, 7 times 30, 5 times 20, and then 5 times 10. And so you can plug all that in and get an approximation for this one is 498. So the two different approximations, if you did a midpoint, guess where it would be? It'd be between these two values. This is a 9, 498. Okay? And I think what we do now is going to do a midpoint one so you can see how that one's done. Okay? So same thing again. And I know what it is. I didn't do the Katie's midpoint one. That's fine. But you get the idea. I think down here I have this one as a, well, I'll just do Katie's. Here we go. So now we're going to do what? Now this one's a little bit harder to do because I need a midpoint thing. All right? Which means I only have so many points. I have 0, 2, 6, 8, 15, 20, and 25. So I'm not going to be able to get 6 rectangles because I need a midpoint. So that means if this is the midpoint right here, this is the 2, 15, 20, and 25. So I have to use 2 of these spaces to represent one rectangle. Since between 0 and 6, 2 is in here, I can take this thing and come up to that distance there, which is 9. Hold on a second. My thing beeped and I don't know why. Well, hopefully I'm still recording. Yes, I believe I am. Sorry about that, but it beeped on me and kind of threw me off. So 9 times 15. And then over here, we're going to have 10 times 20. And we can work this out and get an answer for that. So I didn't multiply this out, so I don't know the answer real quick. And so you guys can figure that out and get an answer as an approximation there. Okay. I want to continue on and I want to talk about the trapezoidal sum now, which is the same, just a variation of the same thing. But instead of doing rectangles, we're going to do a trapezoid. We're going to do a trapezoid in this fashion right here. So I'm going to have the two bases are going to be the ones that go up. Those are the ones that are parallel. This represents the height of the trapezoid. And so this will be base 1 and base 2. And then that diagonal is the other side of the trapezoid. So you see that the sliver here is a lot less. If I do this one, this is another example of a midpoint with the e to the x one. And you can see if I do this one, okay, I have still a sliver above and below. See, I got a part above and below. This one is a lot thinner, so this could be a better approximation for that. So this is what I'm going to do is I'm going to find these two heights, and then this will be that the height of the trapezoid, and these two things are going to represent the bases. Okay, and so we're going to do this one using e to the x. All right, and so let's take a look at that, and let me move this out of the way and go through it with that. So same thing as before. In fact, I'm just going to show you the picture here because I'm running out of time on this video, and so you'll get the idea. Okay, let's take a look. So here's e to the x, 1 to 3. There's our picture again. And so what I do, here's the 6 subintervals again. And so I'm going to go up to the height on each point. Each one of these is going to be a height in here. So I found them all of those heights. We did this table already. And so now I'm just going to do the trapezoidal thing. Notice in each trapezoid, there's a 1/2 and then there's a height. In this example, this height is 1/3 and it's the same for every trapezoid. So I'm literally going to factor that out again. So there's the 1/2. There's the 1/3 for the height of each trapezoid, found using the same formula right there. And then I'm going to just add the two bases. So it's that height times that one plus that one. And then this one plus that one. You'll notice the ones in the middle get hit twice, here and here. See that? But the two edge ones only get chosen once. And so just add up all those things as you go along. And then when you combine all that together, you're going to get an answer. And whatever that is, when you can figure it out on a calculator. Okay? So that's how I would do a trapezoidal sum. This is it, just the formula right there. Instead of an area of a rectangle, it's going to be a trapezoid. So here is Katie's story again. Remember her going to the store or to school. Okay? And so here it is again. Here's the same table. Here's the sketch for it. Okay? And so what I've done is I just made little trapezoids. So there to there, there to there. All these little trapezoids. See, it's all different widths down below. And that's fine. There's no common number. So there's going to be, that number is going to, this height is going to be in each one of these things in here. And that's what you're going to look at. Here's the 1/2. Okay? 1/2. That distance times that plus that. The two bases. That's the first one. The second one is going to have a 1/2. The height is 4, and then it's going to be 14 plus 20, and so forth. And so we just keep doing that for each one of these trapezoids that you see. There are 6 of them, 1, 2, 3, 4, 5, 6, and I get that approximation right there from that. So if you think back to the other two that we had, the left was 471, the right was 498, and this one is 484.5. So you can see that it's between the two, and it could be a better approximation depending on the situations that we have. Okay, so that's how we do a Riemann sum, and that's how we do a trapezoidal sum. Recap it again. Draw a picture, put the dots in for the ones that you're going to do, connect the segments, and draw in your rectangles or draw in your trapezoids at the proper height that you're going to be using, a left or right or whatever. Another question they're going to ask you about is to tell me if I have an overestimate or an underestimate. And this is just basically look at the picture that you have, okay? It depends on the shape of the curve and which pieces, parts you're going to cover. So don't try and memorize it, just understand the nature, how to determine it. So if I have an increasing concave down curve, as you see right here, a left Riemann sum is going to be an underestimate, but a right is going to be an overestimate. And the trapezoidal will be an underestimate. If it's increasing in concave up, so it curves like that, the left will be an under, the right would be an over, and the trapezoid will be an over. Decreasing and down, the left is an over, the right is an under, the trapezoid is an under. And decreasing and up, this is an over, the right would be an under, and the trapezoid will be an over. So just think about that as you draw this curve. Look at this and see, okay, well, which way would it actually be? This will help you solidify in what you're looking at. And we're going to do some more of these together as we do this in class.